we would be starting with Ozone feature set and roadmap. We have recently got a bunch of features, and we are also a bunch of features in the roadmap. So Shiv Murthy would be going over all of the exciting features in the Ozone. And next topic, another exciting topic is on GenAI and Ozone integration. We got a few applications developed. I think one of the application flow would be explained by Swami, and he would present on that. And the next topic, I would let Madhuri introduce about the next two topics, which are about GenAI applications and simplifying orchestration with the multi-cluster Kubernetes. And the next topic would be on multi-GPU, multi-node deployments with Triton inference servers. Ryan would be talking on that topic. And the next topic would be on Ozone CSI. We were working on Kubernetes storage option from like providing Ozone itself as a Kubernetes storage options, like, which provides a read-write many semantics. And the next last but one topic is on Ozone performance. We have made like a significant improvement since then our previous versions. So the Ritesh and Young would be taking over, talking on the topics. By the way, the previous talk would be like the Ozone CSI would be talking by Prashant. The last, but not the least, it's based on Ozone. This is a new feature. Vichu is working on it, and which is like recently merged in open source as well, Apache open source Ozone as well. So let's get started with the first topic. I would be inviting Shiv Murthy to start with. Yeah, Shiv, please take over.
Great, thank you, Uma. I'd like to share my screen now. Yes. Or are you going to present for me? Either way, it's fine.
Yeah.
Okay, so let me switch to sharing. Okay, so let's dive right in and talk about Ozone. My name is Shiv, and I'm with the product team here at Cloudera. And I'd like to share with you a few things today. Most significantly, we'll be talking about why we built Ozone, what kind of feature set and use cases we were targeting, and the roadmap for what's coming next. So these are quite a few exciting topics. And if you have questions along the way, please put them in chat or feel free to interrupt me at any time, right? So what's the motivation for building Ozone? We talked to a number of our customers. We talked to the community. We heard from various partners. And then we realized our biggest customers had decided that they do need to bring some data back on premises, or they had limitations with their existing storage on premises. So they wanted to, the common problems we heard about were dealing with large volumes of data, more and different data than it was a decade ago. And that places demands that HDFS alone cannot address. It needs performance, openness between infrastructures, scalability in volumes, storage nodes, and objects. Of course, all this needs to be safe, and it needs to be safe from a business continuity perspective, or DR. It has to be finally scalable and independent from compute. Right? These were the big guiding lights of our design initiative. So with that in mind, we built Ozone, and it has true full stack integration with the rest of the products that we have. It is a two-in-one hybrid object store that provides the scale of an object store and all the benefits of a hierarchical file store. It has strong security with TLS, TDE, and a single policy engine. Right? And we provide native support for S3 API and Hadoop that enables cloud-native architectures. And as you can see here, the pictorial there represents the range of experiences and services that we support. Now, the open data lakehouse that you've all been hearing about runs extremely well on Ozone. all the compute engines, Impala, Spark, NiFi, Hive, are integrated for accessing and processing Iceberg datasets concurrently. SDX for security, governance, auditing, and lineage is also built in. Iceberg Catalog enables concurrency and ACID transactions, manages schemas and locations. Table maintenance optimizes table performance, and is certified with Ozone storage. So this is Iceberg table format that we're talking about. And ultimately, we did provide features for Iceberg replication for DR recovery and backups. The primary use cases that we are currently seeing our Ozone customers using are deploying applications that use S3 APIs, consolidate clusters into dense nodes and supports up to 500 TB per node, which is 5x the HDFS capability. PVC data services customers interested in separating compute and storage, customers interested in deploying hybrid cloud architecture. These are customers that want to write an application once and run it anywhere, on-prem or in the cloud. Customers running into HDFS scale limits that we talked about briefly before, and customers who would like to put historical data in S3 and use it once in a while. This is the archival workload. So these are the big use cases that I'm hearing every day. And I believe Ozone has adequately addressed all of them. And there are other applications which are emerging every day. Now, we also have been working on making Ozone an extremely performant object store and to support the high throughput of GPUs, and which is essentially AI enabled. You're going to be hearing a lot more about this during the rest of the talk today, right? So basically, performance doubled in just a few months of development, and we're continuing to push the envelope on a regular basis. Today, we can easily read about 200K reads per second. This was achieved using Cisco hardware with 1.2 petabyte NVMe cluster with 40 gig network. We did an 150K mixed workload testing with 10% clients writing and 90% of them reading. So we think it's ideal for AI workloads, which is write once and read many. And like I said, you'll hear a lot more about this during the rest of the talk. We also made Ozone very usable, right? So we built a rich set of dashboards to make monitoring and tuning a large Ozone cluster relatively easy. So Prometheus, which is the metrics service, comes packaged with Ozone, and we have Grafana dashboards, over 200 of them, I think at last count, that we have published. And so using Grafana, you can actually see various pain points in Ozone, optimize your cluster for maximum performance. And finally, the most important part about and the last slide for me, which is the roadmap slide. So here I've highlighted all the things we have already released. These are the current things that are coming out in the next quarter or shorter timeframe, including HBase support for Ozone, which would make it pretty unique because it's a full operational database running on an object store, and that is very, very few and hard to find. Performance improvements, enhanced supportability, recon improvements for better cluster visibility and manageability, including able to do performance management. And finally, multi-tenancy. This has been in tech preview for a while, and we will try to make that GA in the next few months. Looking out ahead, everything from FIPS to building automation for HDFS to Ozone migration, storage tiering, federated storage, and way beyond that is a whole list of things that we're working on. So exciting times ahead, lots of work, and happy to collaborate with you to hear more about what we can build. Thank you.
Hello, everyone. Thank you for joining me today. My name is Swaminathan, and I'm a software engineer at Cloudera, and I'm an active contributor to the Apache Ozone project. So today I'm excited to share how Apache Ozone can optimize GenAI applications. And so what I'm not is an AI expert here. So I will be specifically focusing on how Ozone sits well with RAG use cases and how it can drive efficient AI workflows. So let's move on to take a look at today's agenda. Yeah. So here's what we'll be covering today. To begin with, we would understand what RAG is and how a typical RAG pipeline looks like, and how Ozone enhances GenAI pipelines, and a quick walkthrough and a demo of how everything works together. So yeah, so RAG stands for Retrieval Augmented Generation. RAG is a machine learning technique that combines retrieving relevant documents from a knowledge base uh, with uh, with generative models to produce more accurate and context-aware responses. So in a typical RAG pipeline, we have a LLM model, LLM, a vector database, and a data store which can store a huge amount of training or context data. So this kind of a setup basically helps us bridge the gap between vast amount of unstructured data to context-aware AI responses. So this is how a typical RAG pipeline looks like. We have we have a data store, we have a vector DB, and we have a query engine which basically helps us to query stuff in our context aware data on our data store. So how does Apache Ozone make a RAG pipeline more efficient and easier to implement? So the key lies in how data is stored and accessed. Organizations typically store huge amounts of data, context data in object stores. So Ozone supports both S3 and Hadoop file system like APIs, which basically allows us to seamlessly integrate with existing ecosystems. So Ozone also provides change data capture mechanisms like snapshots to capture the state of your data over time. So these the snap and all of these snapshots can be compared with each other to generate diffs, which can be in turn used to do a pointed update to the indices in the vector DB. So by leveraging all of these such features, Ozone ensures that data is consistently available, and the time spent in updating the database is also minimized, and reducing the overall latency in the AI workflow. So let's see Ozone snapshot, how it works. And let me just get in the whole slide. It's easier for you guys to understand. So Ozone allows you to take snapshots which are consistent across an entire bucket, ensuring that all objects in the bucket at that point in time are captured in a coherent state. So this is especially useful in systems where data consistency is like super critical. In contrary to the traditional object versioning, where changes are tracked at an individual object, in a really highly dynamic environment where multiple objects are constantly being updated, object versioning can become really complex to manage, and especially like if an application, downstream application, requires a consistent view of the entire data set. So with object versioning, each file has its own version, but there is no guarantee that if there are two files which are related, are going to be consistent with each other. So like we can take a look at the example. We have like, say we have like two files. One is like solarsystem.txt and pluto.txt. And then we go on to update this document where like Pluto is not a planet anymore and it's like a dwarf planet. So you could like two different transactions could be updating these documents. So like if we take a snapshot in a consistent state 1 and consistent state 2, we know that both and when we update the vector DB, we would basically be working on consistent state. Unlike like if we directly update our vector DB indices in an inconsistent state, then we could be in a shoddy situation. So in summary, like while object versioning is like super good for individual file tracking, but point in time snapshots really offer a more holistic and consistent view across the object store, which is like super good. So, and yeah. So, and one of the other operations that comes along with snapshots is the snapshot diff, which allows us to compare two snapshots and identify the exact differences between them. So instead of like scanning the entire data set, where snapdiff basically like just focuses on what has changed between the two snapshots, and which makes it like super high efficient. So a typical snapshot diff output would typically have like 4 kinds of entries. Like we'd have a plus sign for a new file that has been created, and a minus sign when a file has been deleted, a modified sign when a file has been modified, and rename when a key has been renamed, a file has been renamed. So like with all of these outputs, we can technically like easily update the vector DB indices to the context aware data. So putting things together. So let us see how all of these pieces fit together to build an efficient RAG pipeline. So we start by like storing the unstructured data in Ozone, and then we can read this particular data through the S3 API, like something like a Python-based Boto3 client or something. And then we have our vector embedding model. Here we are basically using sentence transformer model because like in our particular example, we were dealing with text data. So this could be anything, like the data could be any multimedia data. So technically like based on that, the model vector embedding model can also change. And then these vector embedding models are basically used to convert these unstructured data chunks into vectors. And along with the vectors, we also like put in the reference to the file chunk in Ozone. And then we have a snapshot diff processor, which is basically responsible for taking continuously taking snapshot on the data over time. And like the snap diff basically updates the vector in vector DB like efficiently. And now let's see how the user query flow would look like through the RAG pipeline. So we have a user, and then we have a query engine, which basically like the user can ask a question here. And the question is again like using the same sentence transformer model, we like get the vector embeddings out, and through nearest neighbor search algorithm that is supported by majority of the vector DBs, we get the context chunk information. And through the same Boto3 client, we can query the same from Ozone. And we can like use some kind of a natural language model like Minstrel 7b to generate a natural human-like response from the context data, whatever we have received. So in a grander scheme of things, RAG pipeline this basically can ensure that the data retrieval is efficient, and we have like a scalable storage and also like we are also like minimizing duplication of data over multiple spaces. So yeah, anyone interested in contributing to Ozone, we have the GitHub repo up here, and we have the contribution guide and the Jira link. And we do have a weekly community sync. Feel free to join. So that's all. Thanks a lot.
Good evening, everyone. Thank you so much for attending this meetup and our talk. So I am Selvi Kadirwil. I'm the engineering lead at a startup called Illotl. And we are a seed stage startup. We build infrastructure products for operators to effectively run GenAI workloads as well as generic workloads on Kubernetes clusters. In today's talk, I'll be talking about how you could self-host an LLM and RAG pipeline on Kubernetes. We'll start with why you would want to do so and how you can do so. Okay, so this is the quick agenda for today. We'll start with why would you want to self-host LLMs in your own cloud accounts? There's a plethora of LLM model service providers today. There's more coming up every few days. Why would you want to do it? The first reason is better control of cost. As you know, there's a wide gamut of model shapes and sizes available today. So if you could have a simple 7 billion model working really well for a back-end data processing application, but you might want the latest and greatest models for your customer-facing apps. Using self-hosted LLM will allow you to control both the infrastructure elements and hence the cost of these pipelines. Secondly, better control of performance. If you have used public API service providers, you'll know that rate limiting is a significantly restricting factor. This means that you are unable to provide the right QoS deliveries to your own customers if you depended on these public API service endpoints. And thirdly, you can avoid model lock-in. Despite the fact that there are many service providers, you choose a family of models. If you went with Anthropic Claude models, if you went with Gemini models with Google, if you went with Mistral models, you are restricted to a certain subset of models. If you self-hosted your models, you have a wide variety to be able to choose from. And when new models come out, you're not bottlenecked by your cloud provider or your AI provider to make these models available. And finally, base foundational models are extremely powerful. Typically, these capabilities are extended through retrieval augmented generation or fine-tuning. We focus on the RAG technique. You're able to extend these base capabilities by having the RAG technique. And the RAG techniques involves sharing private internal data with your AI service provider. When you self-host it, you ensure that your internal data is not leaving your organizational boundaries within your cloud account or your on-premise resources. So these are some of the reasons that might apply to you, for which you might want to self-host your LLM pipelines. So how do we do this? So Illotl proposes a simple GenAI infra stack that we will be going through today. We start with the underlying hardware. We do want both CPU and GPU instance shapes from your cloud provider. Illotl's product Luna is the one we'll be focusing on. It's an intelligent cloud agnostic autoscaler. And it runs on all the big four cloud providers, GKE, AKS, EKS, as well as Oracle. We chose Kubernetes as the unifying platform for two main reasons. Its ability to provide portable applications as well as portability and scalability, which was really critical for us. We wanted to allow our customers to be able to right-size their infrastructure choices, and Kubernetes allows us to do that with the addition of Luna. We also chose the Ray distributed computing framework. This is an AI compute engine. It originated in UC Berkeley. It's now used in production in a large number of Fortune 500 companies. The graphic here shows you all the way from OpenAI, Google, Uber, Lyft use these for both training and inference. In our case, we're using a subset of this project called Ray Serve for the model inferencing piece. So we start with the cloud provider, then go to Kubernetes, we use Ray, we also use Luna, and above that we set up your RAG service and deployments, as well as your LLM service and deployments. Okay, so in this talk, Illotl has two particular products, Luna, which is our single cluster autoscaler. Nova is a multi-cluster orchestrator. So even if you did start your generic and GenAI workloads on a single Kubernetes cluster, you'll notice that for a number of reasons, you will need a larger number of clusters for performance, geographic distribution, multi-tenancy, and so on. We'll talk a bit more about that. So you'll see that the graphic on the right, we replace Luna from within a cluster, not replace, in addition to Luna within a cluster, we show you how Nova can help. We'll go into a detailed example showing you how these two products can help set your AI pipelines in production. Okay, so how do we do it? We're going to go with a step-by-step procedure of what we just saw with more specifics. You can start with a Kubernetes cluster on any cloud provider, GUI, command line, once you get your cluster up. Luna is available as a simple deploy script or a Helm chart. You can get that deployed. You'll be able to have the fundamental hardware that's going to be always on. The pieces after this are the pieces that you can bring up as and when you need. So then we do the installation of Ray. Ray runs on both bare metal virtual machines as well as Kubernetes clusters. We use a tool called KubeRay, also provided by the Ray team, which can deploy your Ray cluster. Ray consists of a head node and a bunch of worker nodes, which can be scaled through the Ray autoscaler. Luna comes in at this point when your inference workloads increase. Luna detects this, makes requests for further worker nodes, adds them seamlessly to your Kubernetes cluster, and ensures that your inference workloads performance is maintained. RayServe also uses a project called VLLM, but this is a LLM serving tool. It's also from the Berkeley and Stanford universities. It ensures that serving is fast as well as memory efficient. Typically, that's the bottleneck for fast throughput of your serving queries. At the bottom is our GitHub repo, where we have all of these pieces very easily deployable into your environment. The third step involves converting your data set into a vector database. Elotle's GenAI infrastructure supports two different types of unstructured data formats, text documents as well as web documents. In the case of web documents, it could simply be, say, your company's public documentation site. So you would simply give it a sitemap URL. Our vector DB creation job can parse through these documents and create your vector store. We use Facebook's similarity search library store. This can also be plug and replaced with other vector databases like VV8, DataStax, or Pinecone. So at the end of this step, a Kubernetes job comes up, parses your data, converts it into a vector store that is then available for querying through your RAG service. So that is the final step where you deploy your RAG service. In the diagram, we show you the typical RAG pipeline that the speaker before us talked about. A user comes in who has a query. We first talk to your vector database, find the most relevant documents to that question. This is then retrieved, and then this question, along with the context, is sent to your LLM. The LLM then answers the question based on this private internal data, which has not left your organizational boundary at that point. Okay. So let's look at a demo where what we did was we used our company's Jira dataset. We created a vector store using FAS, and then we queried it to show how easy it is to set it up. The key point over here is that the always on part of this component can be a single instance on, say, an EKS cluster where your Luna autoscaler is running. All of the other pieces can come up as and when needed. So you're making sure that you're right-sizing your resources as per your incoming load. We take a look at the set of nodes. It's got 3 nodes. The base T3 X large is only what you will have always on. The other first 2 nodes, which was a GPU node and a slightly larger CPU node, was brought up when your Ray service was deployed. We'll go ahead. We'll then look at the pods in this cluster. You'll see that there's the kube ray operator, which brought up the Ray head and the Ray worker nodes. The final piece is the RAG LLM deployment. This is where the user query goes in. Then we look at the list of services. Most of these are internal services that you don't need to be worrying about. It's only the final external load balancer service that the URL that we'll pick up. So the 4 apply and help charts resulted in this setup. We then will open up a browser to talk to our RAG query endpoint. Before that, we look at some of the backend that took place. We set up an S3 bucket with our Jira tickets that were first converted into a CSV and then got transformed into a bunch of records. Each record was very simply the field name with the field values. So we didn't require any specialized data processing to get this to this format. After the Kubernetes job that does the vectorization completes, you end up with a single file. It's a small data set, so it's stored as a file in S3. We then open up. We don't yet have a chat UI, so we just use a Postman API endpoint where we ask a question about, hey, what's the description of the most recent security ticket in one of our products that is Luna? And you can see that obviously this information is not there in the base LLM. Relevant documents were picked up from the set of tickets. It says, hey, there was a ticket about requests and limits not being sent for a webhook. This is the latest security ticket. This is an accurate retrieval. We did have a security effort a few months ago, and this was the part of that ticket. We then tried to ask the same question about the other product of ours, Nova, in which case we interestingly noticed that the LLM, it's a Mosaic ML 7 billion model that we use. The choice of model was based on how can we be super cost effective, because we want people to use this as part of their POCs, get this up and running, iteratively develop it, and can always move up in model size. So in this case, the model replies by, hey, the context provided does not specify whether this ticket is a security issue or not. So in addition to making the answer, it says, hey, I might not have had sufficient context. So this opens way for tuning the model, tuning the data processing to say, hey, we might want to use a slightly larger context to get a more accurate result. Okay, let's go back to... Okay, so we looked at single cluster deployments. Luna ensures you're right sizing what type of Kubernetes nodes are being chosen for your running inference workload. When do people go multi-cluster? Typically, without GenAI, multi-tenancy is a big reason. You don't want teams to be sharing clusters. You might not want your customers sharing clusters. You might want multiple products in multiple stages. Your dev, staging, prod workloads are all in different clusters. Once GenAI workloads come in, resource availability becomes a big point of concern. Certain regions might have the GPU node shapes you need. Certain regions might not have it. Further, you also want to deploy your apps in multiple locations to be closer to your customers, to provide better performance and QoS guarantees. This is where Nova, our second product, comes into the picture. It's a multi-cluster orchestrator, which means it takes in your incoming Kubernetes workloads along with what we term as a schedule policy, and maps these workloads dynamically to the right cluster. So Nova's periodically in touch with every one of your clusters. It understands how many of your GPUs are being used, how many CPUs are available. And when an input workload comes in, it knows to redirect it to the right cluster. So it's very similar to how Kubernetes orchestrates workloads within nodes. Nova orchestrates workloads across your clusters. So we have a number of schedule policies. I'll talk about two, which have been most relevant to our customers who want to run GenAI workloads through Nova. One is the availability-based scheduling, which is how many CPUs, how many GPUs, how much memory, how much CPU, when can I go to the particular cluster. The second one that we've just released is called fill and spill scheduling. This one was was motivated by work with Red Hat that we recently did, where they had customers with hybrid environments. They had on-prem clusters with sunk cost of GPU nodes. They wanted to target these clusters first, and when there was a spill or there's excess workload, that's when they wanted to use their cloud resources. So we have a fill and spill scheduling policy that can be defined in Nova to place your workloads across clusters. So here's an example of a RAG pipeline, very similar to the demo we looked at. There's two extra additional pieces on the right. One is called the CADA, event-triggered resource scaling. So what we did in this case was the customer's use case was new data sets would come in that needed to be parsed and converted into your vector database, not just statically at the beginning of your data processing experiment, but over a period of time. So Nova was able to schedule these CADA workloads also across clusters and bring up the vector DB creation jobs as and when needed. This was a talk actually at KubeCon a few months ago, so you could, there are more details about it if this is an interesting use case for you. So yeah, what we wanted to share was a GenAI infra stack that becomes easy to use through Ilotel's Luna and Nova products. We'd love for you to take a look at it. That's our GitHub repo ID. I'm happy to take any questions. What we're currently working on is the ability to add more configuration knobs to both our vectorization and our model serving pipelines. So yeah, happy to take any questions.
Thanks, everyone, and thanks, Selvi, for the great presentation beforehand. I'm Ryan. I'm from NVIDIA. I work on the Triton Inference Server on the engineering team. And today I'm going to talk a bit about scaling deployments with Triton Inference Server. So just to give you a bit of a brief overview. First, I'll explain what Triton Inference Server is. Just a show of hands in the room, how many people have heard of the concept of inference serving? Okay, so a few of you. So I'll give a brief overview of that, how Triton handles it specifically. And then since this is a multi-cluster meetup, I'm going to talk about multiple ways of deploying on clusters. So first, Triton. So similar to Selvi's talk, where you saw their stack that was built around Rayserve as one component for the inference and the serving, Triton is a similar solution in that it is capable of doing inference serving, right? So it's inference serving is composed of essentially hosting models somewhere, hosting some kind of web service to accept requests from clients or users, and then connecting those pieces such that a request from a client goes through, does inference on the model, and ultimately returns a response. So when you use something like ChatGPT and you type in the browser, that's essentially a client taking a request, doing inference through something like GPT 4.0 or something, and then taking a response back to the browser. I'm going to talk a bit about the architecture. In Triton specifically, we have three main components, and we call that the front end, the core, and the back ends. And I'll just do a brief overview of how each of those look. So first is the front ends. This is kind of the bread and butter of the serving parts of inference serving. So in some of the highlighted boxes here, you'll see some components such as our HTTP and gRPC front ends. Triton actually has many, as well as many components in the ecosystem, but this talk will just be focused on the server and clusters. Next, the front ends have to talk to something to handle things like load, scaling, load balancing, and actually scheduling the requests to the correct model to do the inference. So here you have the core components. This is essentially in this diagram, just schedulers, some model management, such as like loading or unloading models, and some metrics for observability, like how your deployment is doing, how long the inferences are taking, etc. And lastly, for the inference, we have backends. So this is the actual part that's doing the machine learning or the AI, right? So this is the frameworks, such as things like VLM, TensorTLM, PyTorch, etc. Triton has an abstraction around all these backends such that you take any backend you'd like, deployed through Triton. It's the same interface through the front end, it's the same interface through the core, and ultimately you get back a sort of uniform schema, regardless of what model you're using under the hood. Now that we have a rough idea of what Triton is, let's talk about actually using it, right? So use case you might have for Triton is to say, deploy Llama 3 on some system and accept requests, right? If you have a service that has hundreds, thousands, millions of concurrent requests, you need to be able to scale this thing to account for the load. So like I mentioned, I'm going to be talking about a few ways of doing this, but first we'll talk about through Kubernetes. So one of the most commonly requested features we've had in the past 6 months, maybe a year, with the rise of LLMs is the ability to serve massive models. So if you take something like Llama 3 405B, that's just a lot of numbers and letters, but what that actually is assuming it's like a FP16 model, that's like 800 gigabytes of GPU memory just to load the weights. And then there's further memory usage required with the KV cache at runtime to make sure that your inferences are running quickly and you're getting a fast response when you talk to ChatGPT or something. 800 gigabytes of memory is not an easy thing to come by, especially on GPUs. And even if you have enough GPUs to do that, it probably doesn't fit on a single node. Like if you have a DGX with 8 GPUs, maybe that has like 600 gigs. So already you need more than one node just to serve this one model. And that was a hard thing to sort of encapsulate a multi-node model as a single logical unit, and then take that unit and scale it out. So what we have in the diagram here on the right is this notion of a megapod, where the pod in Kubernetes terms is actually 2 nodes where they're interconnected. They have many GPUs, all to account for the size of the large model. Then given this megapod, how do we take this and scale it to, say, we have a cluster of many nodes? Well, that's where we have a few of these challenges described at the bottom. So first of all, given, say, 2 nodes to host one model, we need this notion of gang scheduling. So we need both nodes to be ready before they're ready to do anything, right? So if one comes up and one's still spinning, the one shouldn't be doing any work until its partner is ready. Second is, how do those two nodes actually talk to each other? So that's where MPI comes in. I mean, there's many ways to do this, but in the concepts, in the context we have here, assuming Triton and assuming something like TensorRT-LLM, we use MPI to talk. Third, you now have two nodes communicating. You have a logical notion of multiple nodes. How do you create replicas and scale that thing? So that's where this Kubernetes feature came in, the leader worker set, where for every pair of nodes in this example, we define one node, like node 1, for example, as a leader, and the other node as a worker. And this allows us to define all sorts of things, such as if we think back to the front ends and the web serving parts of inference serving, we only want the leader to accept the requests from the client, because the leader determines what to do with the work. If every node took every request, they wouldn't be aware of what everyone else is doing, and the system would sort of get confused. So having only the leader accepting the requests, it can fully dictate all the work that the megapod gets. And same goes for like metrics and tracing and stuff, where if you want to query that information back out. That's the leader-aware load balancing as well. And lastly is auto-scaling metrics. So assuming we have this notion that only leaders report metrics, and we have metrics exposed through Triton, how do we know when it's time to scale? So Triton exposes a ton of metrics by default. All these metrics are at the level of like requests, at the level of models, as well as at the level of the server. Your mileage may vary based on the use case, based on the model, et cetera, but I have a little demo where I'm going to show that we actually take a custom combination of metrics. So we have a notion of queue time, which is how long requests are waiting to get run by the inference engine, and compute time, which is how long the requests took once they were actually scheduled. By taking sort of a ratio of this, we can get a rough idea of how well are we keeping up with the load, right? If the queue time is going up, we need more. And if the compute time is going up, then we're okay. So I have a bit of a demo here. The last time I tried to show this demo, the room was too dark to see it, so I think this will be more successful. No audio required. I'll just talk through it. So on the top left here, for Kubernetes folks, you'll see here's an example of our megapod I was talking about, the leader worker set, where it's 2 pods, 1 pod on each node, and these comprise a single megapod. On the bottom left, we're going to start sending some requests. So this is like the equivalent of typing a prompt into ChatGPT. And then on the right, we have a dashboard tracking the metrics of the deployment, like I was talking about. So this is actually, you can't read the details on the bottom, but this is going to report that custom ratio of time spent in queue versus time spent computing. And we've defined some threshold in our Kubernetes deployment, our Helm chart, to make sure that once a certain threshold is hit for the queue time, we actually scale up. So now you can see the output has gotten much crazier. So in the top left, we've basically identified our threshold has been hit. So more pods are starting to auto scale up. And then we can see our metrics are starting to populate with the additional 2 pods, like the gray and blue, for example. And now we can continue to send requests. We should ideally be able to keep up better with the load. And then similarly, when we cancel the requests, we'd like to scale back down to 1. So we're not like wasting the time. Yeah, so is that a question? Mostly from a cost perspective. So the question, if you couldn't hear it, was why is Triton doing this dynamically at all? If you're doing like an on-prem solution, why not just have all your workers ready to go to meet the needs? Some use cases might not know their needs, or they might not know the upper bound, or maybe it's bursty traffic. And having, in this scenario, like nodes of 600 gigs of GPU memory, just sitting idle, running, waiting to accept requests would be pretty expensive. So the general idea is for scenarios like bursty traffic, we want to support scaling down so you're not wasting money. So it'd be the same as any other Kubernetes auto-scaling deployment, more or less. Like Triton's just a detail in this scenario, but we scale down the pods, and whatever happens after that is up to you as the cluster manager. Sure. Yeah, so the question was, does it take a while to download the Triton image or load the models, et cetera? Short answer is yes, probably. I mean, it depends on your setup. Some setups will have like cached images on like an NFS distributed on all the nodes so that you're not actually downloading, you're actually reading from disk or something, or a logical disk. But yeah, it'll depend on your setup. So sometimes naively, it could take a while to spin up if you like completely cold cache, you don't have anything. But if you're in a real deployment, you probably have some of this ready to go. So there's no general like networking setup assumption, I'd say, if that's your question, like if they're interconnected versus not. Those kind of fall into the realm of like details about TensorTLM in this scenario for how it handles it. But generally, we only care like for a given megapod that all the nodes and workers are available and that they can talk to each other. And from then on, we assume inference will succeed based on the setup of TensorTLM. So just for time, I'll continue to the next parts. Yeah, so that's a brief overview of Kubernetes. I'll take some questions at the end as well. But I'll also talk a bit about Reserve because, like I said, multi-cluster. So here's my second cluster. Similar again to, I'll keep using Selvi's talk because it had a great overview of a lot of these concepts, which I omitted from these slides. So we have a rough idea of what Reserve is. If you think of Selvi's diagram, you could think of Triton as a replacement for that Reserve component in the stack. But we've also recently done some collaboration with Anyscale to show that Triton can actually be embedded into Reserve. So you can keep Reserve in your stack, but you can use Triton's, if you think back to the components, you can use Triton's core and Triton's backends to actually do the inference. So say you want to use Reserve, but you want to use TensorTLM and you don't want to use VLM, you can put Triton into Reserve and let Triton be your uniform interface to talk to TensorTLM. So we'll dive a bit into that. So on the right, we have a rough diagram of what both Reserve and Triton are. I'm not going to go into too much detail on either because I've already spoke about Triton and we have a rough idea of Reserve, but the part I want to focus on is in the center of the two, this dotted green line, which shows a deployment in Reserve and how we use Triton's Python API to implement a Reserve deployment. And if you're wondering why you might do this, well, you actually get value from both components. So from Reserve, you get really easy load balancing and scaling. It's just like Python native, very simple code and some decorators, and you're off to the races. And with Triton, you get, like I mentioned, these optimized backends, a lot of which are written like in C++ and have years of optimizations for real use cases, as well as the ability to use multiple types of backends or frameworks without changes to your deployments. You just change your Triton configuration and the deployment stays exactly the same. So let's talk a bit about how that works with Triton. So that box I highlighted, the Triton Python API, this is just a rough overview of it. So Triton is primarily written in C and C++, but we have bindings to all sorts of languages, and Python is one of them. So what that gets you is, if you're familiar with Reserve and you are writing Python, it would be very convenient if you could just include Triton in Python instead of figuring out how to run C++ code from Python, for example. So we have a in-process handle to essentially that Triton core, which is this Triton server object. We can initialize it. We can do inference on it with simple Python objects like dictionaries and strings and lists. And then we get back responses. And this loop is, as always, performance aware. So the inference is not like some blocking call. It's actually an asynchronous call. And eventually your responses will be populated somewhere else when they're ready. So you can do other work or parallelize while the inference is running in the C++ backends. Lastly, it's performance aware again. So for interoperability, if you like say, Triton is part of some larger pipeline and you're writing some PyTorch or CuPy code or something, you can interrupt between these tensors through the various defined interfaces with zero copy, assuming it's staying on like the same device. So like a Torch tensor on GPU can be brought into Triton without copying it, for example. So let's look at the Ray portion. So as I mentioned, now that we have a Triton Python API, and we want to write a Ray deployment, we just add a couple lines here to initialize Triton. And then we have a couple decorators that Rayserve offers to say this deployment will take 1 GPU, for example. And then that's pretty much it. Rayserve has all the tooling to deploy this thing. It has like a CLI, Ray serve run, for example. It also has like the Kubernetes operators if you want to use it through Kubernetes. And you might be asking, so this is just 1 GPU, kind of simple. How do we do more? Well, once again, just decorators. We can use Ray's auto scaling config, where you just add some more information to the top. We say we're willing to scale from 1 to 8 GPUs, similar to the previous question, where maybe you have more hardware available and you want to pull from that pool. You can take this and say, based on some criteria, we'll scale all the way up to 8 GPUs and back down to 1 when we're done. So this is a lot easier than all of the Helm chart setup we do in the first example. But they have pros and cons. Some are more flexible, some are more powerful. This is just an example showing how it works. So lastly, observability always being important to a real deployment. Is that for me? Sorry, can you mute whoever that is? Cool. Yeah. And then there's also Ray. Did I lose audio? I guess so. I'll keep going anyway. And we have Ray metrics, which are at the level of replicas and queries per second and such. So we can see in this example, this is kind of a screenshot post-mortem of that scenario we had where we scaled up to 8 replicas at some point based on load, and then the load stopped, so we actually scaled back down. And you can see that in the replicas parts. And I believe that is about it. Hopefully that wasn't too much information, but I'll take some questions, yeah.
If I want to add if I want to have things like page detention or maybe speculative decoding or any sort of memory optimizations in terms of how data is moved between GPU, CPU, and maybe cold storage, or even fundamentally I'm trying to understand the benefits of Triton.
Yeah, so I'll take some of your specific examples. Something like page attention is very much like a framework detail. So like both VLM and TensorRT-LM both support it. Through Triton, you get that one interface that you change your config file to say, I'd like to run VLM instead, and both would work. And the frameworks handle most of that. Like during inference, we will make sure to use the GPU efficiently, for example. But Triton is like a layer above where maybe you have multiple models and you're pipelining them. And you want to say, I'd like to efficiently copy the data around or move the data around and avoid a copy. That's where Triton would come into play. And also, be aware that the outputs are here and the inputs are there, and connect it up such that you're not copying if you don't need to be.
So Ryan, we have 2 questions from the chat online.
Sure.
The first one is, what's the benefit of using Triton inference or servers over NIMs? NIMs.
NIM, NIM?
Yeah.
Yeah, so I wouldn't say one's better than the other. They have different use cases. Triton is fully open source and kind of the do-it-yourself kit where you can customize it based on whatever you need and make your own on-prem solution. Whereas NIM is more like the one-click, ready-to-go, highly optimized for certain GPUs, certain scenarios, sort of the out-of-the-box solution without much configuring or tinkering.
Yeah. The second question is, can Triton run on Mac OS, and does it take advantage of Mac architecture for inference?
I'd say macOS is pretty untested right now, and I didn't catch the second.
Apple's native optimizations for inference.
Yeah, so I mean, as a extension of the first answer, not really at the moment. We're always interested in collaboration, and we're open source. So if any macOS users want to try it out or find issues, please raise them, and we're happy to work together.
Thank you.
All right, thank you.
Hey guys, I'm Prashant. I'm a principal engineer here at Cloudera. And then I'm going to be talking about how we can support Ozone in a Kubernetes environment and how we can provide it through native CSI support. So that's the pretty much goal of what we are presenting here. One of the goals that we had was to provide Ozone as a storage platform for our data services, Cloudera data services platform. So for this, we are leveraging the JuiceFS CSI driver. The way it works is it keeps all of the file system metadata on a MySQL cluster. And this MySQL cluster, it comes from the CDP base cluster. Alternatively, it can also be hosted on another key value store like TiKV. The data blocks for the JuiceFS file system, they are actually stored in the Ozone cluster, which is part of the CDP base cluster. Alternatively, this Ozone cluster could also be, deployed on the Kubernetes instances, the server. The advantage that we have with JuiceFS is it's POSIX compliant, it's Apache 2.0 license, just like Ozone, and it comes with native CSI support. So, like, given all these factors, we decided to go ahead with this. So this is the overall JuiceFS architecture. At the bottom layer, you have your file system broken down into metadata and data part. Metadata could be hosted on any of these key value stores. The data part could be stored on any S3 compliant storage. And this is the part where we are using Ozone. On top of that, it has its own in-memory cache layer, a separate cache for the metadata part and the data part. And on top of that, you can expose it through the Fuse interface. So in a Kubernetes environment, this is how it works. So you have a dedicated mount pod on your instances, 8 instances. These mount pods are the one that actually mount your underlying JuiceFS file system, and then through the native JuiceFS CSI driver, it exposes that. This is how we plan to use it in our Cloudera CDE and CML environment. This picture is not complete. Okay. So we have this virtual cluster in which our CD workloads, get deployed, or the CML workspace where your CML pods get deployed. Today we support two different type of storage classes, Longhorn and NFS. This Ozone as a storage class, that is something that we are planning. And this Ozone storage class is the one that's gonna, in the backend, it's gonna use the MySQL on the CDP based cluster as well as the Ozone. So I guess pretty short presentation. Before I move on to demo, do you guys have any question?
Nitin Chawla online has a question about fundamental question. What is JuiceFS and the purpose? I think you kind of covered that. Maybe his question came towards the end, but if you just want to reiterate why JuiceFS on top of Ozone for Kubernetes.
Yeah, so for the native CSI environment, we wanted the files like file systems interface. So today Ozone doesn't have a native file system interface. The other reasons why we chose JuiceFS is we evaluated other options. And then the things that were interesting about JuiceFS was it was Apache 2.0 license, just like Ozone. And it pretty much checks on all the boxes that we had. Let me go back. It's POSIX compliant. It comes with native CSI support. So that all worked out very well for us. Yeah, go ahead.
Go to the next one. So the CSI driver is actually JuiceFS.
Yep.
And JuiceFS is using
Ozone.
something from Ozone
Yes.
as its backing store.
Yep.
And JuiceFS also supports other backing stores that are S3. And so my guess is it's sputtering through the S3 interface on Ozone.
Yep. Yep. So let me move on to a short demo part. So this is our K8 environment on this cluster. This is my base Ozone cluster. And these ECS instances, I will have my K8 pods running here. They will leverage the Ozone. So what we do here is there is a mechanism where you can create a Ozone secret. So basically, this is the part where you give the configuration that in the backend you will be using Ozone buckets. The second part of it is the storage class. So you can create a dedicated Ozone storage class here, just like we had Longhorn. And this Ozone storage class ultimately makes use of this Ozone secret that we just created. And then using this Ozone storage class, you can spin up pods. So I have already spin up a couple of pods here. And let me see. So if you log into one of the pods, what is wrong? It's mounted on /data, right? So I have created some test files here for the purpose of this demo. You come out of it, these are all dynamically created volumes. The backend is Ozone. You can also separately mount it and see it. All right, it's mounted. These are all the different dynamic PVs that are created for these pods. And these pods are available in read-write many mode. So you can share them across multiple pods. Yeah, that's all I have for this presentation. Questions? Yep.
Since you have this other thing in play, is there? Since juice, oh God, I don't like that. Since the juice thing is in between file access and the Ozone, I guess how does the performance shake out versus if you were directly attached to Ozone? Is that a concern or?
Yes, so there will be a latency impact because there is an intermediate layer there, but it's a stopgap solution until we have the native Ozone CSI driver. Yeah.
I guess I'm not an expert on Ozone, but I know S3 is object-based storage, and CSI supports both, I guess, objects and probably more file-based storage.
Mhm.
And you're talking about this as a fuse layer, so that's, to me, implies file-based storage. Does Ozone also have, and I know, basically the object versus file is the access is all is one versus you can modify individual bytes. So the question basically is that a thing that Ozone supports in the backend file, like individual byte changes, or is it all always object-based storage?
It is object-based storage, but then we do have another mode where you can get like very much similar to file system-like interface.
Speak in the mic.
Oh, sorry about that. Yeah. But then if you are going in Kubernetes environment, if you take anything else through the CSI interface, ultimately you will have an intermediate layer that will have to provide a file system-like interface. So if you were to compare it, so think of it as an alternative to NFS. Yeah. Okay. Yep.
Have you tried putting any that large images on it?
Yes, we have maybe Swami. That would be the right question for Swami. He has experimented with that.
Yeah, question is, have you tried putting any large LLM images on it?
Not exactly. We haven't tried that out. We didn't try like the really large.
On GCFS space? No, we haven't tried yet. Yeah.
Not on the JuiceFS, but directly on Ozone.
Yeah, we used Ozone for connecting through the LLM applications via S3 API. Seamlessly it works because we support S3 API. But JuiceFS is mainly the purpose is different semantics to support. So where Kubernetes needs read-write many like semantics, right? Ozone doesn't support natively that read-write many. So that's why this JuiceFS is an additional layer where it provides native file system semantics like NFS or any other file systems. Yeah. Yeah, there is one more question, Prashant. From which version of Cloudera data services would Ozone CSI be available?
So that's something that is still in plan. But if we have something, we will share it soon. Yeah.
Thanks, Prashant.
Right. Yeah. Thanks. Thanks, everyone.
Hello. Is everybody good to start on the next talk or any breaks in between? Okay. You guys have been hearing about Ozone on and off, and one basic question comes up is why does Ozone exist? Right. One of the two main reasons why Ozone exists is performance and scale beyond the features that they have. Ozone. So this talk is going to be like an overview of the architecture of Ozone. Talking about what's unique about Ozone over existing storage systems, and kind of talk about the scale and performance of it and the journey that we have been on. Ozone is an Apache project. It's a first-class top-level Apache project. What does that mean? That means the community owns it. We have contributors all over the world. And in such a context, the performance and scale journey is interesting. And we kind of touch about the various paths that we had to take over the years to get to where we are. So Young and I are going to present. Young is remote and I will be in person over here. So at a very high level, what is Ozone? Ozone is a storage system on which a customer or a user can use the Hadoop file system API or the S3 APIs and store data. So for companies such as Cloudera, it's very interesting because they have, I don't know, thousands of exabytes of capacity under HDFS. They have it's a common day thing for us to have customers call up about a 100 petabyte cluster. So scale is there. It's all under the Hadoop file system API. For data processing, the next big API is not POSIX, but it's S3. The amount of data stored in behind the S3 APIs for data processing is probably dwarfs anything else out there, right? So naturally, as a next generation of storage product, you have to get those two APIs in the door. Very similar to a lot of storage systems, we have a dedicated metadata layer, a distributed metadata layer, which is managed by Ozone Manager. And Ozone Manager gives an interface, an object-based interface, which can work for Hadoop file system API as well as S3. These objects consist of data that's stored as blocks, and those blocks live in containers. And that's where the front-end story ends, right? So as far as the customer is concerned, he's storing data in objects. When he looks at the metadata for the object, he sees that the data is residing in containers. They have and the containers are on some nodes. But who's managing the container to node mapping? Traditionally, metadata systems would have a single metadata layer, which would manage not only the user-generated metadata about files, directories, hierarchies of objects, but would also maintain where it's stored in the cluster. In Ozone, we have split the architecture, wherein there is a dedicated layer that handles the front end and a dedicated layer that handles the back end. What that means is that we have separated the concerns of scaling front-end load from a customer and scaling the backend capacity that needs to be managed. What that means is you can have billions and billions of small files or exabytes of capacity under a few million files. And Ozone scales for both use cases. That's because we have separated the concern about what does it mean to have a backend that scales hundreds of racks and each node's having hundreds of terabytes of capacity under its management, failures that happen, rebalancing of capacity, growth, day to maintenance, taking down nodes. All of those scale challenges are dealt with the storage container manager, which is in between. So you can see the storage container manager kind of sits in between the data node and Ozone manager. And Ozone manager only cares about how many IOPS does a customer want. It doesn't matter what the object size is. Right? Each of these layers have their own version of high availability. Ozone Manager and Storage Container Manager are backed by Ratis, which is the Raft implementation. It itself is the top-level Apache project that is used by multiple companies, not just Ozone. So if you have a Java project out there and you want a Raft-based implementation, definitely go check out Ratis. We also have one of the main contributors of Ratis in here in the house. If you have any questions, Nicholas is in the house. So the backend can be erasure coded or can be replicated depending on what the customer wants. So that's the high availability story on the backend. So this gives the high level architecture overview of what Ozone is. There are, of course, a lot of details, but for this talk for 20 minutes, that's good enough. User sees volumes. So we have created a hierarchy where you have volumes. A volume is a namespace of buckets, and buckets are very traditional to S3 buckets. What that means is you can have your data application in development having a data set which goes into staging, which goes into production. So you can have your data move through volumes, and your application development happens in one, then you promote the data to staging, you promote it to production, right? Each of the data can be optimized for file systems such as HDFS, or it can be optimized for object store. So when you create a bucket, you have a choice. Do I want a file system-based bucket? What does that mean? That means you get atomic renames. S3 API does not have atomic renames, right? Which is a big thing in data analytics, in jobs, when they want to move in files that have been processed into production. You won't have that atomic rename guarantees. You want directories. You want to be able to list directories. And there are certain smaller fineness about having file system APIs that S3, you can kind of fake it, but it's not really there when you really care about the guarantees. So what we do is we give you a choice. You can have a bucket that's file system optimized, and it works perfectly well for Hadoop, or you can have an S3 style key value store where you just have prefixes and objects that are attached to it. Again, talking about the separation of concerns, the Ozone client, Ozone manager only cares about customer generated load, and data node scales out. It kind of handles both the front end and back end, and SCM just cares about background. There is no foreground load on SCM. So you could have an SCM that's very busy without customer generating any data because a rack failed. And subsequently, you can have an Ozone manager which is very busy while SCM is not doing anything because the cluster is nice and happy. And we have a service called Recon, which is kind of like a join between the backend and foreground. So you can kind of see which keys are in which containers on which data nodes. Those kind of analytics are done by Recon. It's a very interesting project that's we introduced in Ozone that traditionally you don't see in storage projects. Now, coming back to so I hope this explains why we scale. Now coming back to performance and testing, right? So obviously we don't have thousands of nodes sitting around for testing. Unfortunately, we don't have the budget for that. So what we do is SCM just cares about data nodes and the payload they send to it. It doesn't actually know that there is exabytes of capacity. Each data node only scales to the number of drives. So you can kind of break down the problem into how do I test a data node? You scale up the number of drives, you fake it out, and you get your per node scale. When you go to SCM, you fake out the heartbeat information. You say, there are 1,000 nodes. Each of them have 400 terabytes attached to it. And as far as SCM is concerned, that's the reality, right? So even though we have taken on a big challenge, we have ways to break down how we scale and test it. And we had, let's see, one sec. We have been doing very poor with demos because videos are not playing cleanly. But you will have to believe me that there is a video attached. Hopefully this plays over here. And Okay, looks like it doesn't copy. Essentially, okay, it did show up. Nice. So this is the Recon UI where you can see we have HDFS, the fact that we get to 1 billion objects is a big deal because you don't have to deal with heap management. You don't have to handhold a cluster. It just happens on its own. Okay, now I'm going to hand it over to Young. Young, can you unmute yourself? Hopefully you can. If not, let me try. Okay, Young, can you try and unmute yourself?
Hi, do you hear me?
Okay, yes, we can.
Thank you, Rotes.
Yes.
Yeah. Hi, everyone. My name is Sean. I'm a software engineer in the Cloudera storage platform. I also am a commit of the Apache Ozone project.
Young, you'll have to go closer to the mic. Your volume is pretty low.
Okay. Let me change the microphone. Is it better now?
Yes.
Hey, Rotes already introduced. Ozone was built from the ground up to address the scalability issue from AWS. But as always, the architectural, even with those architectural benefits, the details of the implementation make the work of difference. And yeah, just like other projects, open source, we started fast and incrementally going back to revisit our decision in the past to bring performance stability to the level that we expected. And yeah, and in the past couple of years, we have been focusing on improving the scalability and performance of the Ozone Manager, which is the metadata layer. And after a while, we got some satisfying result from the metadata layer, and now we're shifting our focus on the data IO itself to fasten the performance of the client to data nodes data transfer. Okay, and yeah, I'm going to the details of each of the Ozone performance projects. And yeah, so here is some details around Ozone Manager scaling. So in the last 2 years, we have successfully improved the performance of Ozone Manager metadata rate from 10K operation per second to 200K operation per second. And that is not an easy way. It has been a rough way to reach that level of scalability. So below is some detail regarding the projects that we take. We implemented a container location cache in Ozone Manager. This is because as described in the previous session, we have a separation of concern between Ozone Manager and SCM who manage the data nodes. So every metadata request, we need to Ozone Manager to go to SCM. to fetch the block location. But with this catch, it will eliminate all of those things. And also there is optimization on the security side. We use symmetric encryption to replace the built-in asymmetric encryption to make the performance feasible for hundreds of thousand operations per second. And also we optimize the locking mechanism using stripe lock. And on the other front, we also optimize list key by selectively given by omitting the block location from the payload size and that reduce like around more than 95% of the payload size, and it's make a world of difference in the list key performance. And in the right front, we also have different optimization to push the key creation rate from 2000 at the beginning to 7 to like more than double the performance of key creations. Can you go to the next slide? And for now, we are shifting our focus to the data part, the data transfer part from client to the data node. And and one thing that we immediately noticed is the data transfer protocol. So for now, Ozone is still using gRPC for data I/O from client to data node, and this gRPC is running with protobuf, and by default those have a significant drawback. It pass the protocol pass any incoming data as protobuf object in the heap zone. So this imply serious consequences because it's imply multiple copy in allocation and pressure to the GC cost. So we have been addressing that by applying zero copy in gRPC in different part of the data I/O. So the part of writing to EC is already done upstream, and we are still in the progress to make the Ratis write part work for Ozone. Can you go to the next slide? So a little bit about details about zero copy in gRPC. You see here in the on the right on the left side. So before every piece of incoming data will be received in the read buffer in the NIO zone, and then the gRPC will need to parse the incoming data as a protobuf object in the JVM heap, and that implies one copy and heap allocation. And also in terms of when Ozone writes the data to the storage disk, it will NIO will need to do another copy to write before writing the data to disk. So this implies multiple copies and allocation in the heap zone, and thus also imply the hit to JVM garbage collectors. And can you keep it there? Follow. Yeah, and recently gRPC now support zero copy. You see here the optimization is pretty simple. So we can reuse the incoming read buffer and to do our logics and use the same buffer to write to the disk. So this eliminate completely the two copies and one heap allocation. And yeah, can you go to the next one? Yeah, and as a result, we see around 20% improvement in I/O, but this is only for our test environment. And we also see a survivable JC cost and the possibility to saturate network or this bandwidth, whatever the lower capacity. And so this improvement in the data part is crucial because it is crucial because nowadays the hardware is becoming faster. And we also have a requirement to have more disk in the same data node for for lower operation cost. So it is crucial for the application layer to handle the data, most efficient. Can you go to the next slide? Yeah, and another project for optimizing data I/O is rapid streaming, and this one is already available on upstream. So a bit details about rapid streaming in this project, we avoid using wrap log replication to write data from client to data node, and instead we build a custom implementation on top of Netty and NIO to optimize the right path. And this one we avoid the gRPC path by default, and because of that we can leverage 90 zero copy from Netty. And the detail of the implementation of rapid streaming also enhance network topology awareness and optimize the round trip of the of data transfer. So yeah, this one is itself is a massive project, and yeah, we have Nicholas here in the room for any question regarding this streaming. Can you go next? And from the gRPC zero copy and rapid streaming, I think we got a good lesson about the use of gRPC in our data I/O, which is used today for both read and write across all the components. And one future project that we believe once done will put the performance of Ozone data I/O on top of the chart between any other data storage products. So we would want to consolidate on the I/O part across all the components, including client and S3 gateway data nodes, to just use to implement a custom I/O protocol on top of Netty and NO. And with that, we leverage the 90 zero copy support from I/O and also have a granularity control on how the data is flowed for on the use cases. And we expect to apply the same thing for read and write and also rebalancing data between data node. And yeah, this one will be a huge project. But we ambitious to take this one because it's crucial to our I/O performance. Yeah. Yeah.
Any questions on Zoom or in the house? Yep. You can go speak up. I'll repeat the question.
Lisa from Impala. So Impala has a good performance against HDFS because we cache a lot of things from file system like block metadata, right? Is Ozone now in the place where Impala doesn't need to cache it anymore and just keep asking metadata to Ozone, or we still need to cache it?
So the network latency is always going to be there if you don't cache it, right? The benefits you get from caching is the fact that you don't have to go over the network every time you want to get a piece of metadata. So those laws of physics benefits of caching will still apply. right? If you compare Ozone versus HDFS, I think erasure coding, we are slightly faster. In replication for writes, we are a little bit slower, and reads are about comparable. So most benchmarks, we are like 10 to 15% range of HDFS, and there's no other storage system that compares to HDFS when it comes to analytics on-prem. So with regards to your questions about Impala's need for caching, if you are just doing a seek over the network, you'll probably see comparable performance between HDFS or Ozone, if not faster. But you still are going over the network, which would be the dominant cost. So I would expect you would still see benefits of caching locally, so that you don't have to go over the network.
Thank you.
There was a question about CSI and whether we have stored large models. In that model, the file system structure is stored with, like, say, one of those in-memory structures or SQL databases. So in terms of your stat or low latency, your backing store for one of those stores would be the function. But in terms of aggregate bandwidth or aggregate capacity, you would be getting what Ozone offers. So you could store really large models using that. But if you want like a file system benchmark of metadata operations, then you'd be subject to JuiceFS's metadata layer. But from a sheer capacity standpoint, it would be Ozone's benefits. Yeah.
I think with the interest of time, we'll move on to the next session.
There is one question online. Ozone performance looks very promising. Great. Okay. Thank you, Venkat.
Yeah. Vichu will be talking on HBase and Ozone now. So Ritesh will be around. If you have questions on that performance talk, you can have a discussion. Thanks.
That should be good, right? Okay, so thank you for staying till the very end of the meetup. My name is Wei Chu. I'm going to make sure quickly to go over the last. Yeah, no. Oh, sure, via Zoom. My bad on that. Yeah, so the last topic I want to talk about is HBase. I'll quickly go over that in maybe 5-10 minutes. So this is a project we've worked on the past 2 years. So just want to highlight things that a lot of hard work our teams are working on. So HBase, for those who know, is a NoSQL database, very scalable, very low latency. You can scale up to petabytes of scale, hundreds of nodes. A lot of customers are using HBase for a lot of production web applications services. The problem that we're having is HBase is very tightly coupled with HDFS. And so there's not a lot of room to innovate. And so our team wanted to help with HBase to make sure that it can keep up with the innovation we have in Ozone. So what we want to do is just replace the HDFS with Ozone, like that. Sounds simple, right? It actually is not. It took us 2 years to get this right. So yeah, I think what we did is we spent about 2 to 3 months to come out with a POC, basically to implement the missing file system APIs that we don't have in Ozone. And then we started benchmarking. And what we realized is that we had a lot of gap to catch up. Because what happens is that HBase for every region server, it has to do tens of thousands or even tens of thousands of file system updates to the data nodes. What our POs did was just around 10 to 40 transactions per second. It's very, very low. So we have a lot of room to catch up. So that's where we embark on almost 2 years of endeavor to try to catch up with what HDFS can do. I'm not going to spend the next hour to spare you time, but I just want to say that a lot of work has been done over we have about 6-8 people working on this project, and in the end, we were able to improve the throughput by about 100x, actually more than 100x. Yeah, so some of the lessons learned we had was developing the storage system can be easy, relatively speaking, but making it optimized for different workloads and computer engines is really hard. It's like a 10x harder. So don't try that at home, and quick iteration is the key. Release plan for this feature, a lot of customers are asking about this feature. It's going to come out in the 7.3.1 of Cloudera and the tech preview coming up very soon. In open source, we are going to have that added in HBase 2.6.1 and also in Ozone 2.0 that's coming out soon. So I want to, in the interest of time, I want to give a quick demo of just putting everything together and see how that goes. I have that demo recorded, so I don't have to set out everything from scratch. So what you're seeing here is we install HBase and a cluster on top of Ozone. So you just specify the different roles and services on the hosts, and then do the regular things. But now you just add Ozone file system instead of the HDFS, and that's all you have to do. And just restart the cluster, and you're done. And then after that, you can install Phoenix. Phoenix is the query layer to query your data, the HBase data on Ozone. So we made that happen as well. So all you have to do is just add a new service, the Phoenix service on top of HBase. Now HBase runs on Ozone, so everything just like connect together easily. Really not much to do, except having that. And then we can create tables using the Phoenix. And then data will be set on top of HBase and Ozone. So here we create a sequence table that's we're going to use for the, I'm going to demo a web application next, and that's going to be used. And next is a table to store user data. I'm going to create a web services to store user data for the application. So now switch to the web design. Create a simple Python web application that's using HBase, Ozone, Phoenix as a backend. And what you can do is very simple. Just insert new names and new year of the user. And now the data has been inserted. I will be able to query the data directly from Hue. And you can find the data is there like that. And then you can also delete data, and that will get reflected in the backend database as well. And not just that, we also made the replication work. So the data, all the updates you made on the source cluster will also reflect on the destination cluster as well. And yeah, that's pretty much it. If you have any questions, I'm happy to take any questions.
So why was HBase support for Ozone a separate item when Ozone already supports Hadoop file system API?
What's the question again? Sorry.
Why was HBase support for Ozone a separate project, even though Ozone supports Hadoop compatible file system? What were the challenges going to HBase support?
Yeah, so there are a number of file system, Hadoop file system APIs, such as HSync, HFlush, and some of the things that's more like HDFS specific that we didn't have in the file system interface. So what happens was the Ozone came out as an object store and has the object store semantics. What HBase requires is additional extension semantics that's not available for the typical object store. So we may have to do additional things to make that happen for Ozone. Okay. So HBase, the question is, what about HBase on S3? So that is a different story because what HBase does is HBase has a basically two kinds of files: the H files and write hello files. Write hello files doesn't have it requires the HDFS semantics that's not available in S3. So that's where we spend tons of time to make that work and performant. So they are, so like Cloudera or some other companies has the edge-based services in the cloud. But what they do is they have the write-ahead log stored in other cloud object stores, cloud stores like Amazon has the EBF, I think. So that's a different story. All right, I think that's it. Anything you want to take it away?